If it goes faster, the point spacing is far. The rows of scan lines are farther apart, that lowers the point density. So if the plane would speed up, the color would go down to maybe green or yellow. Maybe because the pilot needed to go to the bathroom, you know, and said, I better go home quickly now. Then you could see lower point density, and that would be something you would complain about, because you want the blue to be everywhere. And if there was an area that is not blue, because here in this case blue was 5. Sorry, I'm messing this up. You don't see it in this one. Blue was 5 or lower. So if you have lower density, you don't actually see that here. In the other image, there was another one, this one here. This one here. This one is 5 points per then. 5 points. If any of these lines, instead of red, would be completely yellow, or even yellow with blue, going down to close to 0 or 1, then you would know you have one flight line that does not have the required density. And here you see the density is roughly the same everywhere. The only differences come from the turbulence of the aircraft. Okay. So where do we stop in terms of working on the LiDAR data? That was part of the quality check. But I think we already started working on the LiDAR data. So let me have a look. Oh yeah. What was that all about? What did we do here? The noise. These points are pink, because pink, for my particular program, pink is a color that is used to show noise points. Noise points have the classification code 7. I don't know any stupid way of making a joke about this now. Maybe you can tell me you want to think of something. Where do noise points come from like this? Well, okay, I must be more careful with my jokes. It's not all butterflies. Also, it's a nice way to imagine the world full of butterflies. It can also be just, if it's a very sunny day, sometimes the sun happens to be in the same spectrum as the laser wavelengths, and you just get sort of random glares. But it's also likely to be humidities, or just a oversensitivity in the scanner. Particulates, yeah. But this is very nice noise because it's so obvious and very easy to remove with last noise. We went through 3 iterations to refine it a little bit, make sure we didn't delete the power lines on the ground as well, and then we could classify all the noise. Remember, after I removed the noise using dropped classification 7, the bounding box was not changed. So then afterwards, I used last info minus repair to fix the bounding box. Last info minus repair, if you run that on a file, it doesn't create a new file. It just looks what the bounding box is and recomputes it and sets it to the tightest possible bounding box according to the points. What we did then, I think, is ground classified the points. And on these tiles, we did do the bounding box. So we writing it out. Remember, I wasn't sure if that's going to work because I never tried it before, using drop classification 7 together with last round, but apparently it did work. And afterwards, we made the bounding boxes to be a tight fit to the points. Then we ran tiles, then we classified the tiles. And the results were sort of mixed. This looks like a pretty good example where I look at here right now because the houses are sort of nicely sized, and this is clearly a tree. Maybe this is a tree and not a house. I can't tell. And a reasonable way to tell it, make the visual check easier, is by just selecting the first returns and triangulating them, because then the trees and the housing roofs suddenly look very different. So, yeah, it's hard to tell, but yeah, it actually looks correct. This is probably a house. You see, it finds a house right among all the trees because the house is planar and the trees jumps up and down the points. We didn't spend a lot of time playing with the parameters here. That goes a bit beyond the scope of the course. But I explained the 3 parameters to you that are available in the last classified window. GUI. What do we do then? Oh, there we stop. We didn't create the final tiles yet. What was the final tiles all about? Or why is there still a step to be done? We were out of time. It was 6:02. Well, actually, we weren't out of time, but the clock made me think we're out of time. Because it's wrong, it's fast. What is that last step? To create the tiles that are sort of ready for delivery. No, to create the LiDAR tiles that are ready for delivery. Because a lot of your customers will not just want the DTM, especially in LiDAR 2 projects. Delivering the point cloud is important because there's much more information in the point cloud than you have in the DTM or the DSM. So, and I will talk actually today about, I hope Philippines will open that LiDAR data, not just to a select few individuals with deep pockets, but to everybody. And I'll show some examples from other countries why that may make sense. What did we do when we tiled the data? We created tiles and we made the tiles a little bigger. Why did we make the tiles a little bigger? We created a buffer of 50 meters around every tile. Why?
To remove the errors.
To move the errors away from the real boundary into the boundary we were gonna cut off later. And that cut off later we haven't done yet. Because the final tile should be 1,000 by 1,000 meters and not 1,100 by 1,100 meters with some dirt in the outer 50 meters. And I'm not sure I can show this because it doesn't happen always. I showed you on my one tile, the Busa dot. You see if you see some of these misclassifications here along the boundaries. Maybe that's a bad example. And nothing really on the boundary. could be one of those cases. Here we see a roof, and the roof isn't fully classified. It's right on the boundary. That could be one of the places where it is the fault of the lack of information on this side that made the algorithm not include that into the planes. Okay, so the first thing we will do, we will remove the boundaries. And need my magnification glass. So the tool to do that is LAStOOls. LAStOOls can create the boundaries, the buffers, sorry, and you can also remove them again. LAStOOL. I hope you still have your data from yesterday. And I hope you still find your data from yesterday. So my data is right here, the sample data folder. I don't know, 1 kilometer. Tiles final. No. Tiles classified. So here we have the tiles that are classified that still have the buffer. And now there's a way to remove the buffers. We go into a different mode. We're not going to tile, we're going to remove buffers. Remove buffer points. And then we put the output in the directory tiles final. Say use current. I think that's it. See, that's really it. So last tile. The final tiles, in my case, I want to use the classified ones. If you didn't want to do the classification step for some reason, you may do the same thing with the last ground, tiles ground. And then it's important that you have this keyword here, minus remove buffer, and this is where the tiles go. And all that's going to happen now is the buffer's get removed, and afterwards, those classifications that are likely wrong, or have a more higher probability to be wrong because they're along the boundaries, they're no longer part of the data. But you have all the data because we created an overlap beforehand. And now we just remove that overlap between the tiles. Okay. Now, now we want to create DTMs, and we're going to do this in 2 different ways. First, we're going to create a DTM for every tile. And for this, we need new folders. So I must make a new folder in here called tiles DTM and tiles DSM. What's a tool to create DTMs and DSMs? After them. That is when I want to create in a tile-based workflow. Every tile is one DTM. But when I want to create a tiling of DTMs. So I'm quitting. I guess I already quit it. So I'm looking for last to them. So I want to first create the DTM. Agno, 1 kilometer. The DTM, it's a bare earth terrain. Which data should I use to create the DTMs? Of all these?
Tiles ground.
Okay, tiles ground, I can use those. Which one can I also use? I can use the classified ones. Correct. What about the tiles final? That's a bit of a trick question. The points in tiles final have no error. But the points in tile final are all exactly inside the entire tile. There is no point outside the tile. Now if I'm making a rasterization and I triangulate only points that are inside the 1 by 1 kilometer, what can happen in the very, very corner of a tile? There could be a missing pixel. And if there's a lake, and you know, those poor returns that never came back, there could be actually not just 1 missing pixel, there could be 10 missing pixels. And if there's a river, there could be a lot of missing pixels. Because we need some supportive points around the tile that are actually not in the tile. And therefore, we want to use the tiles with the buffer. And then use the option, use tile bounding box, use tile DB, to like cookie cut out only the center. So that the tin is definitely nice and big enough around the tile, and is supported everywhere where we're gonna raster it. So, I take tiles ground, I'm adding it, and now before I forget it, remember, once I forgot it, I talked about it and I didn't use it. Use tile bounding box. I'll check that first. We will create real DTMs at this point, so the actual values. Elevation, step size. 1 makes sense because the green LiDAR data is flown with the target of creating 1 meter DTMs. We have 2 shots on average per square meter, and sort of common sense dictates you should be able to get a decent 1 meter DTM out of that. I'm running on multiple cores, and I'm putting the output into the tiles DTM directory. One more important thing is to select the output format. A lot of people like to use the ASCII format because it's very simple. It's not very efficient. I recommend using the BIL or the TIFF format instead. They can easily be converted to ASCII. and they are much more efficient. So let's use the TIFF format. What have I forgotten so far? Huh? Filter. What kind of filter? Keep classification. Which one do I want to keep? Okay. Awesome. Keep classification, 2 and n. Alright, now let's create some DTMs in the Philippines. After them, my input, just double check. It's the ground classified ones. I'm running on 8 cores. I keep only the ground points. I do raster the elevation values. I'm only using the pixels that fall into the tile bounding box. Also my tile is a little bigger than the bounding box. I output it into this directory in this format. Now on my computer, 8 processes running in the background, and it's done. Because we had a bit of a problem to look at these, because I didn't know how to learn QGIS and I didn't have time to, to make the shading look nice in QGIS, and I didn't have time last night. Let's make the DSMs as hill shades. Now usually you would make both the same time, but this is an exercise. So we use hillside shading for the DSMs. I just need to change the name of the output directory. This seems a lot of work going in there, so usually what I do, I just go in on the command line and put it S instead of the T, because that's faster than opening the browser, browsing, say use current, because I know how to edit the command line. And of course, what do I need to do in order to create DSMs? I want to hear it from this direction. I need to filter. What do you need to filter? On first returns only, exactly. So I'm removing this by double clicking. And I filter on first only. And then I say run, and let's see what I get. Oh, I forgot one thing, and I will see it soon. Well, I didn't really forget it, but I like to use a different file format. So, last of them, list of files, course 8, first only, I'm making a hill shade now. That's a picture. I'm using this new output directory. If you still have a T here, you can just change it to an S. That was, it's actually much easier than, and it still says TIFF. Now TIFF is also an image format. I could use TIFF, but I noticed that in Google Earth, PNG looks a lot better because it has better transparency support. So in areas where you don't have anything, it's transparent. And with TIFF, sometimes it's black. So I like PNG better. TIFF, however, would also work. And then I say start. is already done, and I have a look at it by going to my DSM, and yay, I have KML files everywhere. And if I find my Google Earth window somewhere, it is. I'm dragging and dropping my 10 tiles on here, drag and drop, and clack, 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 clack. Here I have my beautiful DSM overlaid on top of everything else I've done so far. And a very interesting thing to observe here. What is this? There's something funny, looks like a big oil spill or something. Anybody who has an idea what this could be? Anybody who thinks it looks familiar? Overlap. But why do I see the overlap in the hill shading? What is hill shading? Hill shading is putting an artificial light source somewhere and then shade the surface. Now when you look at surfaces, the shading is not only defined, it's not at all defined by the elevation, it's defined only by one thing. It's defined by the angle to the light source on a macro level, and on a micro level it's defined by the roughness. So, just look at water, if it's flat, it's perfectly mirror. I mean, that's a different example. If it has fine ripples, it looks completely different. Same with the field. The field is the farmer just went through the field and then puts a grain on the field, or what you see here is the ripples in the overlapping flight lines. You have more points here than anywhere else. The triangles here are much smaller. The illumination, the color, is computed based from the norms of the triangles. Triangles are smaller, they are more unstable, they are more likely to shift left and right and up and down. With tiny, tiny elevation differences can make a huge difference to the direction the triangle is facing. So there is more roughness in this area. If the flight lines are bad aligned, really bad aligned, this will look like corn husks, or maybe like a rice field, where it will sort of look like rows of rice planted when it's really poorly aligned. But this is actually fairly good aligned. In order to create nice looking hillshades that are more production quality, you shouldn't create the hill shading, and I mentioned this before, from the point cloud, because a point cloud has different densities. It's higher density here, and this creates this artifact. You should first make a raster, like a bill or an ast or a tiff, and then apply hill shading to the raster, because when you have a raster, the points are evenly spaced, and every triangle has the same size, and they don't wiggle around anymore because of tiny, tiny little elevation differences. These triangles are tiny, they're sometimes, I guess